man, we got ourselves another fantastic, wonderful, exciting, and kind of complicated application problem. So I couldn't be tackling this one alone. I had to have myself some River Dog Jenny over there. What up, Jenny? She's like, what are you doing, man? Well, anyways, we're going to hop to it here. Jenny's tuckered out. You know, she's had herself a rough puppy day, as they say. So time for a little bit of math, and we'll see if we need some questions from Jenny here later. All righty. We got Offset. Has a side hustle company that manufactures various shipping containers. Their company slogan is, looking to offset your costs? Look no further. That's great. He is currently working on a new design for an open top box with a square base and a volume of 40 cubic meters. In order to offset costs, he orders a base and side materials from 2 different companies. Megan Trainor sells the material for the base, which costs $15 per square meter. Quavo, one of his Migos, sells the material for the sides, which costs $10 per square meter. Quavo is giving him the 3 Migos discount, right? You know, gotta hook him up. What dimensions should the box be to keep costs below $1,000? Holy guacamole. We got a lot going on here, okay? So most of our problems will be likely set up for us. It won't be quite as involved in this one. But what I really wanted to convey in this is the application aspect, like how we can actually use the math. And it's often a bit more complicated than we'll really ask in class, just because it can get so overwhelming and so over the top quickly. But I think it's something that we can also look into the different parts, and I will point out the types of questions we will ask in our class that are a part of this. Okay, so without further ado, River Dog Jenny and I are gonna hop to it. Sound good, Jenny? Sounds good. She's excited. She's excited. Okay, how about this? First thing, let's draw a picture of this box. So I have a square base box. Let's see here. So I'll do a square base like so. Actually, you know what? I'm going to do, because I know it's going to be hidden. Okay. And then I've got these heights that are a little bit different. Let's see here. They're different than the base. So this one is open top. That's why I stopped drawing that one, so that it'd be like, hey, and now it's hidden. Okay. These take a little bit of practice to draw. I mean, you can see I was even having a slight struggle there. Alrighty, so we've got ourselves a diagram, right? And it says it's a square base. So that means my dimensions of the base are the same. So I'm going to throw an X down, which would make this an X as well. And then my height will be this. So it doesn't really prompt us for like, make a function as, you know, of X and blah, blah, blah. But let's think about it. That's what we're going to have to do if we want to analyze something like this. I got to get this into terms of one variable. Well, let's see what kind of information I have. I know my volume. I could write a volume function. I'm going to do a different color here. So I'd have my volume is equal to length times width times height, which would mean in this problem, volume is equal to x squared h. And I know that my volume is 40. So maybe I can do something with that. I'm gonna pump the brakes on that for now, and then I'll come back to it. Okay, so that would be my volume. And then we're talking about our cost of making this box. Like, what are we making this out of? It might be metal, it might be wood. I don't know. Let's say it's metal. But what I'm really trying to find here is my surface area to know how much metal I should have, right? So let's say we'll do a surface area in a different color. How about, so we'll say surface area. So my surface area would be my square base, which would be x squared, right? X times x. And then each one of these sides is x times h, right? X times h. This one here is x and then a height of h. So I have 4 sides that are x times h. I don't really even need those parentheses. I'm just going to go with this. Okay. So there's my surface area function, right? I'm just adding all the sides for surface area, but there is no top. So I'm leaving it as just 1x squared. There aren't 2x squareds. All right? So far, I think so good. Now, in order to analyze these types of problems, I want this in terms of one variable. I can throw it into my TI-84 Plus graphing calculator if I do so, right? So which one should we mess with? Well, how about over here, I'm going to get this as a function of x. Okay, so I'm going to solve this one right here for h and then substitute that in over here so I can get a function just of x. Alrighty, so how about I divide, let me get that other color going again. I'm going to divide this by x squared. Lovely. And then that would make h is equal to 40 over x squared. So now let's start forming our real awesome, fantastic surface area as a function of x. I'll just call it area as a function of x. I can substitute that in. I'm going to have x squared plus 4x, and then in place of h, I have 40 over x squared. Wonderful. So something we've had you guys do is, and I think we've done it before, is writing these, right? Writing the equation. That was from our polynomial unit. Okay. But this is now, well, let's simplify first, but I'm thinking we've got ourselves a rational because we have something in the denominator. If I do so, I'm going to have a of x is equal to x squared, and then I got 160. The x will reduce, so I'll have 160 over x. Now, I don't have to do that to use this, but I decided to do a little bit of simplification. I'm happy with that right there, okay? Okay, so there's my area as a function of x. Awesome. I do indeed have a rational, and this is actually going to have an oblique asymptote, you'll see. That's fun. Woo! Awesome. So now I'm going to head back into the problem, okay, because I want to double check some things. So I've got an area as a function of x, and I could try to find like the minimum surface area that would give me that 40 cubic meter volume, right? Minimum. That would, if I have my minimum surface area, that should minimize my cost as well, right? But the materials are two different prices, and really all it's saying is we want to keep the cost below 1,000. Okay, so just minimizing the area isn't going to answer this question. I want to keep dimensions or costs below $1,000. Okay. And I've got two different costs going on here. I have the cost of the base material and the cost of the sides, right? So I think I need to incorporate that into my overall function here. So I'm going to annotate this in. So the cost of my base, which is right here, that's $10, right? And the cost of my sides, this is one side right here. That would be, this is 15. And this is 10. Always double and triple check, yo. Right, Jenny? Always double and triple check. Okay, she agrees. Okay. Lovely. So I can pop that into my function here to make it a cost function. So how about this? C of x, new function, new color, add in the cost. I'd have $15 times whatever my area of the base is, and then I'd have $10 times whatever those areas would be. All right. Wonderful. Fantastic. Awesome. All right, because this section here would be my base. This is all my sides. Base, sides, base, sides, right? And then I can pop my costs in accordingly. All right. Jenny has left me, and she now wants to go outside, I think. But that's all right. We have math to do, and then we'll go outside. All righty. Okay. Let's see here. I'm going to do a little bit of cleaning up here. So I got 15x squared plus, and then I have, we're going to pop another 0 on there. 1600 over x. Awesome. So this is now my cost function. I want to know when is this cost below $1,000. I think it's time to bring out the graphing calculator. I'm going to pause it while I plug it in. You do the same. Alrighty, so I've got my function plugged in there, 15x squared plus 1,600 over x. Wonderful. And we want to keep the cost below 1,000. If we remember from past problems, that means that I'm going to throw in another equation of a horizontal line that is 1,000. That way I can find where it's below that in this case. Oftentimes we want to be like above in profits, but we want to be below in cost. So those words are important, right? So I'm going to hit zoom, and then we'll go with fit, which is 0. And let's see what the calculator gives us. Come on, big money, big money. All right. Well, it's not too bad. Okay, it's a little hard to see that 1,000, right? So I'm going to need to make some adjustments. Let's do that. Window. I'm going to go ahead and, wow, 30,000. I am in no, I'm not really looking that high up, right? I'm going to be generous and even just go like 5,000. And then for this, I do not really care about this. I'll keep a little bit. Just, I don't know why. Aesthetics, maybe. I feel like I don't want to completely negate it, but we really don't need anything below there. I feel like I just usually like to see my axes, so that's why I threw that there. All right, that looks a lot better, right? We can see what's going on there. We can see our intersections. Awesome. I mean, I could even have brought it in a little bit more, but I think this will do for us, okay? So I want to find out when costs are below, which is this portion right here. And you know what? I'm actually going to zoom in a little more just so I can write on it and stuff. All right, so here's my new window. I adjusted the X max to 15, and I adjusted my Y min and max in case you want to replicate it. And that's what I have for my graph. Okay, so I'm going to screenshot this after we get some numbers here, okay? So I have, I want to find my intersection points, right? Because it's when it's below, that's when the costs are below 1,000. Okay, so let's go ahead and do some calculations. I'll do the first one together, and the second one, I'll pause. So I have intersect. So I'm first curve, that's just my first equation. Boom, and now I got my second line. And then I'll hit enter again, and voila. I always like to make sure that it is on that intersection. I want to make sure that it's there. So I've got 1.6698. So if I'm rounding to 3 decimal places, that's actually 1.67 because the 8 would round the 9. So we end up only having 2 decimal places there in that one, comma 1,000. So let's jot that down, a 1.67. Okay. And then I'm going to get the other one there when I pause the video. All right, for this one, I got 7.2009, so that 9 would round the 0 up to a 1. So 7. Woo. Lovely. That was the ice maker, if you heard that. I was making some more ice here. So those are my 2 ordered pairs for when that when that function is below, right? So what does that really mean here? All right, so I've taken a screenshot of the graph here so we have it handy. So I'm looking at this portion of the graph, right? So if this would be my dimension, this would be my cost, right? This is my x dimension. So it's just the dimension of the base. So right now, in this scenario, I have, I'm going to go with another color here. So I feel like we've been using this one for a while. I'm going to go red. All right. So I'd have one set of dimensions could be 1.670 by 1.670. And how would I get my height? Well, I would plug it into my function right here. So let's do that. So when I plug in 1.67 in for x into that height equation, I get 14.3425, so 14.343. These are all meters. So we're talking about cubic meters. And then let's do the other one here. So I would plug in, so I'd have 7.201 by meters, 7.201 meters by, and then we got to go ahead and plug that in. And voila, there we go. We get 0.7739, so 0.771. So we have quite the vast range here of sizes for our box, right? We can have a base that's 1.6 by 1.6 and anything up to 7.21 by 7.21. And then our height would obviously be adjusted accordingly to fit this cost of below $1,000 to manufacture. But realistically speaking, like, you know, so even we could have like, say, 3 by 3 by something, we would just plug into our height function to figure out that height, right? That would fit that mold, that would give us that volume. If I multiply these three together, I end up with 40 cubic meters. And same with these three, I'd get 40 cubic meters. Although it's going to be slightly off because we did round these final dimensions. But this would be our range here, right? Anything between these, or our domain, so to speak, I guess, since we're talking X values, but between these numbers, right? And then substitute into this function to get your final height. Really, I think a company would be more so focused on the minimum cost while maintaining that volume there. So you would likely just be trying to calculate your minimum, but perhaps they wanted to have a range of them of it's going to be this volume. We're going to be restricted by this cost. We want to keep it under $1,000. We want to make sure it's 40 cubic meters, but really then the sizes can vary, but they're still fixating on those two things. Volume of 40 cubic meters, cost of below $1,000. The actual shape of it can vary based on what the customer wants, but at least they're going to keep those two pieces under control. Okay, so it just really depends on what the problem calls for, but we're somewhere in here with these, and although it's not like one single answer, again, like I said, it could be, there's a lot of different answers here, but really when you think about it, that's kind of how the world works. Usually there's not like one set solution. We're going to say, hey, something between these, okay? If you're going to go with a 1.670 by 1.670 base, your height's going to be this. If you're going to increase that base, you can't go over a 7.201 meter base because then you're going to exceed that $1,000 cost. Okay, there we go. I like it. We have just helped offset some future costs for not only his company but also other companies. That was awesome. I had a great time. I think Jenny had a great time. She even came back, didn't you, Jenny? There you are. All right. Well, we're going to go play outside now, and I hope you guys have a fantastic day. America, freedom, rock and roll, Costco, and River Dog Jenny. All right?